What lies beyond the edge of the universe? Our observable universe, a sphere, some 93 billion light-years across, represents merely the fraction of the cosmos visible to our current technology, a limitation imposed by the speed of light and the universe's relentless expansion. But beyond this horizon, countless mysteries await, from the possibility of an infinite universe to the tantalizing concept of a multiverse. The questions surrounding our cosmic place continue to challenge our understanding of space-time and reality itself. Understanding these boundaries and the potential beyond is not just a scientific endeavor, but a journey into the very nature of existence, a quest that resonates with humanity's deepest curiosity and drive to explore the unknown. We stand at the precipice of the known, gazing into the vast, inky expanse of the cosmos. But how far can we truly see? The answer, surprisingly, isn't simply a matter of distance, but a complex interplay of light-time and the very fabric of space itself. Our vision is not unlimited. It's bounded by a horizon, an invisible barrier beyond which the universe remains hidden, at least for now. This boundary is not a physical wall, but rather a consequence of the finite speed of light and the expansion of the universe. Imagine shining a flashlight into a dense fog. You can see the beam for a certain distance, but beyond that, the light is scattered and absorbed, leaving the rest shrouded in mystery. Our observable universe functions similarly. Light from distant galaxies travels for billions of years to reach us, carrying with it precious information about the universe's past. However, the farther away a galaxy is, the longer its light has been traveling, and the farther that galaxy itself has receded due to the universe's expansion. This limit of our vision is what astronomers call the particle horizon. It's not a fixed distance, but rather a constantly expanding sphere, marking the edge of what is currently observable. According to current estimates, this sphere has a radius of approximately 46 billion light-years in every direction, giving our observable universe a diameter of roughly 93 billion light-years. Everything within this sphere, galaxies, stars, nebulae, and the faint afterglow of the Big Bang, is part of our current cosmic view. Beyond this boundary, however, lies the unseen universe. This doesn't mean that nothing exists there, but rather that the light from those regions hasn't had enough time to reach us. Galaxies could be forming stars, could be blazing, and potentially other structures or phenomena entirely alien to our current understanding may exist beyond the cosmic veil. The accelerating expansion of the universe, driven by dark energy, only deepens this mystery, pushing those distant regions further and further out of reach. This cosmic expansion isn't simply galaxies moving through space. Instead, space itself is stretching, carrying those galaxies away at an ever-increasing rate. Many galaxies are now receding from us faster than the speed of light, making their light forever unreachable. This is the cosmic event horizon, the ultimate boundary of what we can ever hope to observe. Therefore, defining the cosmic horizon isn't a simple matter of specifying a distance. It's about understanding the interplay of time-light and the dynamic nature of space in a universe constantly in motion. A universe that continually challenges us with its inherent mysteries beyond our current comprehension. Our everyday experience shapes our intuition about space. We live in houses with walls, cities with borders, and countries defined by lines on a map. It's natural then to imagine space itself as a kind of giant container, something that exists within something larger. But this intuitive understanding breaks down when we consider the universe at its grandest scale. According to our current understanding of physics, space isn't contained. It is the container. It's not something sitting inside a larger space. It's the very fabric of reality, the stage upon which the cosmic drama unfolds. Asking where space ends is akin to asking what lies north of the North Pole. The question itself is fundamentally flawed. The very concept of a boundary becomes meaningless when applied to the entirety of space. This isn't merely a philosophical point. It has profound implications for our understanding of the universe's structure. The idea of a finite universe with an edge implies a beyond, a region outside of space itself. What would that even be? The absence of space. The absence of existence itself. These are questions that push the limits of our imagination and challenge the very foundations of our scientific models. Einstein's theory of general relativity revolutionized our understanding of space, revealing its dynamic and malleable nature. Space isn't a static background, but a flexible entity that can bend, warp, and curve under the influence of gravity and energy. The universe's shape, whether flat, spherical, or saddle-shaped, is determined by the distribution of matter and energy within it. This means that even the concept of straight lines becomes relative depending on the overall curvature of space. Therefore, to truly grasp the universe's vastness and mysteries, we must abandon our earthbound intuition of space as a contained entity. Space is the boundless arena of cosmic events, the dynamic medium through which galaxies move, stars are born, and the laws of physics govern the unfolding of the universe. It is not a vessel, but the very substance of reality itself. This fundamental shift in perspective is crucial for understanding the concepts we will explore throughout this journey. Whether the universe is infinite, extending endlessly in all directions, or finite yet unbounded, curving back upon itself in ways we can scarcely imagine, the very notion of a cosmic edge requires a complete re-evaluation of what we mean by space. The next section delves into the fascinating hypothesis of an infinite universe, a concept that challenges even our most sophisticated mathematical tools and stretches the limits of human comprehension. The concept of an infinite universe. A cosmos without boundaries, stretching endlessly in every direction, is both awe-inspiring and profoundly challenging to our intuition. Our everyday experience is firmly rooted in the finite. We encounter edges and limits everywhere we look. Yet the observable universe, vast as it is, offers tantalizing hints that might support this seemingly paradoxical idea. The uniformity of the cosmic microwave background, CMB. The faint afterglow of the Big Bang is one such hint. The CMB's remarkably consistent temperature across the entire observable sky suggests a universe that was once incredibly uniform and perhaps infinitely large. If the universe were finite, we might expect to see greater variations in temperature, reflecting the uneven distribution of matter and energy. However, the relative uniformity of the CMB has been interpreted by some scientists as suggesting a potentially infinite expanse. Of course, this is a matter of ongoing scientific debate. The observable universe only represents a fraction of the cosmos, limited by the finite speed of light and the universe's expansion. We can only see as far as light has had time to travel since the Big Bang. What lies beyond remains a profound enigma. However, the relative uniformity of the observable universe raises the interesting question of whether the patterns we observe extend indefinitely beyond our cosmic horizon. The implications of an infinite universe are profound. If space truly stretches on without end, then every possible arrangement of matter and energy given enough time and space would inevitably occur. This includes the possibility of countless copies of our own universe, even countless copies of ourselves, a concept that stretches the very notion of individuality and uniqueness. While this concept often referred to as the Level 1 multiverse, raises profound philosophical questions, it remains a hypothesis, not an established fact. The infinite universe hypothesis, while not definitively proven, is a powerful and thought-provoking idea that continues to inspire scientists and philosophers alike. Its exploration necessitates a profound shift in perspective, requiring us to move beyond our human-scale intuitions about space and embrace the breathtaking possibility of a boundless cosmos. But it is crucial to remember, while the evidence supports the possibility of an infinite universe proving, it definitively remains beyond our current observational capabilities. Imagine a being confined to the surface of a sphere, like an ant on a giant beach ball. No matter which direction the ant travels, it will never encounter an edge. The surface curves continuously, allowing for endless exploration without ever reaching a boundary. This seemingly paradoxical concept, finite size, no edge, is one model used to describe the universe itself. This model proposes a universe with a finite volume but no discernible boundary. It's not infinite in extent, possessing a definite, albeit potentially vast size. However, unlike the intuitive notion of a sphere with a clearly defined outer surface, this finite but unbounded universe lacks an edge where space simply ends. Instead, space curves back on itself in higher dimensions than we can directly perceive, creating a continuous, seamless whole. This concept is deeply rooted in Einstein's theory of general relativity, which describes space as a dynamic entity that can bend and warp under the influence of gravity and energy. The overall shape and curvature of the universe are dictated by the distribution of matter and energy within it. If the universe's density is precisely at a critical value, space would be flat. If it's slightly higher, space would curve inward like the surface of a sphere. If it's lower, it would curve outward like a saddle. The finite but unbounded model neatly avoids the philosophical conundrums associated with the idea of a beyond in an infinite universe. There is no outside to consider. However, it does introduce the intriguing question of the universe's overall volume. If the universe is finite, then what are the implications for the total amount of matter, energy, and information within it? Could it eventually reach a state of maximum entropy, a heat death that is both absolute and finite in scope? While the observed flatness of the universe, as suggested by measurements of the cosmic microwave background, CMB, initially favors an infinite model, this observed flatness doesn't definitively rule out a finite but unbounded universe that is simply too large to perceive its curvature in our current observational window. The ongoing quest to understand the universe's precise shape and size continues to be a critical area of cosmological research. This exploration of the universe's potential finitude leads us naturally to our next topic, the profound influence of Einstein's theory of general relativity on our understanding of cosmic geometry. Before Albert Einstein's theory of general relativity, space was largely considered a static, unchanging backdrop for the universe's events. Newtonian physics treated space as an absolute three-dimensional grid, providing a fixed framework within which objects moved. However, Einstein's revolutionary work fundamentally altered this understanding, revealing space as a dynamic and flexible entity. General relativity describes gravity not as a force, but as a curvature of space-time, a four-dimensional fabric encompassing both space and time. Massive objects warp the fabric of space-time around them, creating a gravity well that influences the motion of other objects. Imagine placing a bowling ball on a stretched rubber sheet. The ball creates a dip, and nearby marbles will roll towards it, mirroring how objects are drawn towards massive bodies due to gravitational effects. This curvature of spacetime has profound implications for our understanding of the universe's geometry. The overall shape and curvature of the universe, whether flat like a sheet of paper, spherical like a ball, or hyperbolic like a saddle, are determined by the distribution of matter and energy within it. This means that the geometry of the universe is not fixed, but rather evolves over time as the universe expands and the distribution of matter and energy changes. Measurements of the cosmic microwave background, CMB, the afterglow of the Big Bang, provide crucial information about the universe's overall geometry. The patterns observed in the CMB strongly suggest that the universe is remarkably flat on a large scale, although subtle curvatures are not ruled out. This flatness, in turn, informs our models of the universe's potential size and ultimate fate, an important factor in distinguishing between a finite and an infinite universe. General relativity's insights, therefore, are not merely mathematical abstractions, but critical tools in our ongoing quest to understand the universe's shape size and its ultimate destiny. The elegance and power of Einstein's theory remains central to our ongoing exploration of the cosmos. This understanding of space as a dynamic, malleable entity shaped by gravity and energy sets the stage for our exploration of the observable universe and its limitations. Next, we'll define the boundaries of what we can currently observe. Our understanding of the universe is fundamentally limited by the speed of light. Light, while incredibly fast, is not instantaneous. It takes time to travel across the vast cosmic distances, and this finite speed imposes a crucial boundary on our observations. This boundary, the edge of what we can currently see, is known as the observable universe. To comprehend this limit, consider the age of the universe. According to the prevailing cosmological model, the universe began with the Big Bang approximately 13.8 billion years ago. Since then, light has been traveling outward from the initial expansion, carrying information about the early universe. However, because the universe itself is expanding, this light has traveled a much greater distance than we might initially assume. The distance light has traveled since the Big Bang defines the furthest extent of our observable universe. This is not simply 13.8 billion light-years, because the universe has been expanding throughout this time. By the time the light from the most distant objects reaches us, those objects have receded further due to this continuous expansion. Current estimates place the edge of the observable universe at a radius of approximately 46 billion light-years, resulting in a diameter of roughly 93 billion light-years. This observable universe isn't a static entity. As time passes, light from increasingly distant regions eventually reaches us, expanding the observable sphere. Yet the universe's accelerating expansion, driven by dark energy, creates a countervailing effect. Galaxies beyond a certain distance recede from us faster than the speed of light, meaning their light will never reach Earth, regardless of how long we wait. This represents the cosmic event horizon, a boundary not just of current observability, but a fundamental limit on our potential future observations. This section helps us understand that the observable universe is not a fixed entity. Rather, it represents our current glimpse into a far greater and still largely unknown cosmos. Understanding this dynamic boundary is crucial to appreciating the challenges and possibilities inherent in exploring the universe's vast expanse. Next, we'll examine the concept of the particle horizon, a more precise definition of this observable limit. This brings us to a more precise definition of the boundary of our observable universe. The observable universe isn't just defined by distance, it's fundamentally constrained by the speed of light. This constraint, while seemingly simple, has profound implications for our understanding of cosmic scales and the limits of our observations. The particle horizon precisely defines this limit, representing the furthest distance from which light has had time to reach us since the Big Bang. Imagine the universe as a rapidly expanding balloon with galaxies scattered across its surface like dots. As the balloon inflates, the dots move farther apart. The light from each dot represents its history, its story told in photons. However, the light from more distant dots hasn't had enough time to reach us since the balloon started inflating. The particle horizon is like a circle drawn around a particular dot, us, on the balloon's surface. It encompasses all the dots whose light has reached that point. The particle horizon isn't a static boundary. It expands with time as more distant light finally reaches us. However, the universe's expansion isn't uniform. It's accelerating due to dark energy. This means the most distant galaxies are receding from us faster than the speed of light. This creates another more profound boundary, the cosmic event horizon. While the particle horizon represents the current limit of our observable universe, the cosmic event horizon represents the ultimate limit of what we will ever be able to observe, given the relentless acceleration of cosmic expansion. The particle horizon, therefore, is not merely a boundary of distance, but a boundary of time. It's the furthest point from which we can receive information from the past, a snapshot of the universe. At the moment those photons began their journey. This distance isn't fixed. It grows with time, but it constantly reminds us that our view of the cosmos is profoundly limited, a compelling reminder that the vast majority of the universe remains unseen, unexplored, and perhaps forever unknown. Understanding this light-speed boundary is critical to our ongoing efforts to map and interpret the universe's history and structure. This understanding of the particle horizon as a light-speed boundary naturally leads us to consider the profound implications of the universe's expansion. Let's explore how this expansion affects our understanding of cosmic boundaries. The discovery that the universe is not static but expanding revolutionized our understanding of cosmology. This expansion profoundly impacts our concept of cosmic boundaries, blurring the lines between what is observable and what remains beyond our reach. The very notion of a fixed edge to the universe becomes increasingly problematic in light of this continuous expansion. Imagine dots drawn on a balloon. As you inflate the balloon, the dots move farther apart, not because they are inherently moving, but because the space between them is expanding. Similarly, galaxies in the universe are not simply moving through space, but are being carried apart as space itself expands. This expansion isn't uniform. It's accelerating, driven by a mysterious force known as dark energy. This accelerating expansion has a significant effect on our ability to observe distant parts of the universe. While the particle horizon represents the current limit of what we can see, the accelerating expansion pushes galaxies beyond our reach, even those whose light has already begun its journey toward us. Many galaxies are receding so rapidly that their light will never reach us, no matter how powerful our telescopes become. This is the essence of the cosmic event horizon, the ultimate boundary of what we can ever hope to observe. Therefore, the expansion of the universe challenges our intuitive understanding of cosmic boundaries. The observable universe isn't a static sphere, but a dynamic, expanding region constantly evolving as light from ever more distant objects eventually reaches us. The accelerating expansion, however, fundamentally limits the information we can ever access, creating an uncrossable barrier beyond which lies the vast unknown. The universe's expansion, therefore, is not just a fact of cosmic history, but a defining characteristic of our ability to understand it, underscoring the immense scale and dynamism of the cosmos. To better grasp this concept, let's turn to a helpful analogy. The concept of a constantly expanding universe can be challenging to visualize. Our everyday experiences are grounded in a seemingly static world where objects maintain relatively fixed positions. To overcome this intuitive hurdle, let's employ a helpful analogy: the inflating balloon. Imagine a balloon with several dots drawn on its surface. These dots represent galaxies within the universe. Now, begin inflating the balloon. As the balloon expands, the dots move further apart. Crucially, the dots themselves aren't moving across the surface of the balloon. Rather, the surface itself is stretching, increasing the distance between all the points. This is analogous to the expansion of the universe. Galaxies aren't simply traveling through space. Instead, space itself is expanding, carrying the galaxies along with it. The distance between galaxies increases, not because they're actively moving away from each other, but because the fabric of space is stretching. The balloon analogy effectively illustrates this key concept. The surface of the balloon represents the three-dimensional space of the universe, while the dots represent galaxies. As the balloon inflates, representing the universe's expansion, the distance between the dots increases. However, this analogy has its limitations. The balloon is a two-dimensional surface, while our universe is three-dimensional. Also, the balloon has a defined outer boundary, while the universe, depending on prevailing models, may or may not. Nevertheless, the balloon analogy serves as a powerful tool for visualizing the expansion of space and how it impacts the distances between cosmic objects. This visualization helps to demystify the abstract concept of universal expansion, providing a tangible framework for understanding how our observable universe's limits are both dynamic and inherently restricted by the physics of light and space. This simple analogy illuminates a profound cosmic reality. This leads us to consider the profound philosophical implications of an infinite universe. If the universe is truly infinite, extending endlessly in all directions, the very concept of an outside becomes profoundly problematic. Our everyday experience is shaped by boundaries, the edge of a table, the horizon on Earth. We are accustomed to thinking of things as being inside or outside of something else. However, if the universe encompasses all of space, then the notion of something existing outside of it loses all meaning. Imagine trying to define what lies north of the North Pole. The question is nonsensical because the North Pole represents the furthest northern point. There's no further north to go. Similarly, if the universe is infinite, there's no outside because there's no further expanse beyond it. The universe in this context isn't a contained object within a larger entity. It is all of space encompassing all possible locations and directions. This challenges our intuitive understanding of space and existence. We naturally seek to understand our place within a larger framework, a container that provides context and meaning. But an infinite universe dismantles this framework. It presents a reality without boundaries, without an outside to define or contextualize our position within it. This doesn't diminish the universe's vastness or mystery. Rather, it elevates it to a level beyond our ordinary comprehension. The sheer scale and boundless extent of an infinite universe require us to reconsider the very questions we ask about its nature and our place within it. The question of what lies outside an infinite universe becomes not a question of physics, but of metaphysics, forcing us to confront profound philosophical questions about reality, existence, and the limitations of our human perspective. The concept of an outside in such a context may not be simply an unanswered question. It may in fact be a fundamentally unaskable one. This philosophical shift in perspective is crucial as we delve into the relativity of direction within the cosmos. Let's explore how our familiar notions of direction break down on a cosmic scale. On Earth, we have a readily available frame of reference for direction. We have a clear up and down defined by gravity. We have north and south determined by the Earth's magnetic poles, and east and west determined by its rotation. These directions are deeply ingrained in our everyday experiences. However, when we shift our perspective to the universe as a whole, these familiar concepts lose their absolute meaning. In the vast expanse of space, there is no universally defined up or down. Gravity acts locally, pulling objects towards massive bodies, but there is no overarching gravitational field to define a cosmic down. Similarly, the concepts of north, south, east, and west are rooted in the Earth's specific geometry and orientation. These terrestrial directions have no relevance in the context of the universe as a whole. Consider the Earth itself. On a large scale, it appears roughly spherical, yet for any given location, one can define up as the direction away from the planet's center. This direction changes completely depending on your position. This same principle extends to the cosmos. Any specific direction one points towards a distant galaxy, for example, is relative to our position and orientation within the universe. Therefore, the directionality we perceive is always contextual, contingent on our point of observation within the vast expanse of space. There's no objective universally applicable, up, down, north, south, east, or west, to guide us in navigating the cosmos. The concept of direction itself becomes inherently relative in the boundless arena of the universe. This fundamental relativity of direction challenges our anthropocentric view of the cosmos and requires us to embrace the immense scale and complexity of the universe. It is a profound aspect of cosmology that forces us to think beyond our human-centric frame of reference. This relativistic perspective is crucial as we attempt to quantify the immense distances involved. Quantifying the distance to the particle horizon. The boundary of our observable universe requires a nuanced understanding of both the age of the universe and the effects of its expansion. It's not a simple matter of multiplying the age of the universe approximately 13.8 billion years by the speed of light. The universe has been expanding throughout its history, and this expansion significantly alters the distances involved. The light we observe from the most distant galaxies began its journey billions of years ago, when those galaxies were much closer to us. As that light traveled, the universe continued to expand, increasing the distance between us and the source of that light. Therefore, the current distance to those galaxies is far greater than the distance the light itself has traveled. Astronomers use sophisticated techniques based on our understanding of redshift and the universe's expansion rate to calculate these distances. By measuring the redshift of distant galaxies, the stretching of their light waves due to the expansion of space, scientists can estimate how far away they are. However, these calculations are complex and depend on accurate models of the universe's expansion history, including the influence of dark energy. Current estimates place the particle horizon at a radius of approximately 46 billion light-years in every direction. This means that the diameter of our observable universe is roughly 93 billion light-years. It is important to emphasize that this is an estimate based on our current cosmological models and observational data. As our understanding of the universe improves, particularly our understanding of dark energy and the universe's expansion rate, this estimate may be refined. This vast distance, while mind-boggling, represents only the portion of the universe we can currently see. Beyond this boundary lies the vast unknown a testament to the scale and mystery of the cosmos. It underscores the ongoing quest to better understand and measure the true extent of our universe. Having established the scale of the observable universe, let's now delve into its contents. Our observable universe, while vast, is not a uniform entity. It's a complex tapestry woven from a rich array of structures, each with its own unique characteristics and history. Mapping this cosmic tapestry requires a multifaceted approach, combining observations across the electromagnetic spectrum with sophisticated theoretical models. At the largest scales, the observable universe exhibits a remarkable large-scale structure. Galaxies aren't randomly distributed, but tend to cluster together, forming filaments and walls, separated by vast, relatively empty voids. These structures, revealed through extensive galaxy surveys, reflect the initial density fluctuations in the early universe, amplified by gravity over billions of years. The distribution of galaxies isn't uniform. Instead, it follows a complex web-like pattern, reflecting the universe's underlying gravitational structure. Within these galactic structures, we find individual galaxies, island universes of stars, gas dust, and dark matter. Galaxies come in various shapes and sizes, from spiral galaxies like our own Milky Way to elliptical galaxies and irregular galaxies. Each galaxy harbors billions or even trillions of stars, each with its own unique properties and potential planetary systems. Observations of the cosmic microwave background, CMB, the afterglow of the Big Bang, reveal the universe's earliest moments, providing insights into the conditions that ultimately gave rise to the large-scale structures we observe today. Tiny temperature fluctuations in the CMB, detected by missions like WMAP and Planck, represent the seeds of these structures, the initial density variations that gravity amplified over cosmic time. Furthermore, the observable universe contains vast regions of intergalactic space, relatively empty voids, where matter is far less concentrated than within galaxy clusters. These voids are an integral part of the universe's large-scale structure, shaping the overall distribution of matter and influencing the evolution of galaxies. Mapping this complex interplay between galaxies, clusters, filaments, and voids requires sophisticated observational techniques and sophisticated theoretical modeling, demonstrating the immense complexity and breathtaking scale of the cosmos we inhabit. This intricate cosmic web, however, only tells part of the story. Let's now turn our attention to the echoes of the universe's earliest moments. This brings us to the cosmic microwave background. Peering deep into the cosmos, we can detect a faint, pervasive glow, the cosmic microwave background, CMB. This isn't starlight. It's the oldest light in the universe, a relic from a time just 380,000 years after the Big Bang. Before this time, the universe was a dense, hot plasma opaque to light. Photons couldn't travel freely. They constantly scattered off charged particles, preventing the formation of a clear image. As the universe expanded and cooled, however, it eventually reached a point where atoms could form. This crucial transition, known as recombination, allowed photons to decouple from matter and travel freely through space for the first time. This ancient light, stretched by the universe's subsequent expansion into the microwave portion of the electromagnetic spectrum, is the CMB. The CMB isn't uniform. It possesses subtle temperature variations across the sky, tiny hot and cold spots revealed by highly sensitive instruments like the WMAP and Planck satellites. These minute temperature differences aren't random noise, but represent the seeds of the large-scale structures we observe in the universe today. The initial density fluctuations that gravity amplified over billions of years to create galaxies, galaxy clusters, and the cosmic web. By carefully analyzing these tiny variations in the CMB, astronomers can extract a wealth of information about the early universe. These measurements provide crucial constraints on cosmological models, including the universe's age composition and expansion rate. The CMB, therefore, is more than just a faint glow. It is a powerful window into the universe's infancy, offering valuable clues about its origins and evolution. It's a cosmic time capsule preserving the echoes of the Big Bang and providing a foundation for our ongoing efforts to understand the universe's history and structure. The CMB is a fundamental element in our understanding of cosmology, a direct link to the very beginning. However, even the CMB has its limitations, leaving us with many unanswered questions about what lies beyond our current observational capabilities. Let's explore some of these intriguing possibilities. The limitations of our observational capabilities, imposed by the speed of light and the expansion of the universe, leave a vast expanse of the cosmos shrouded in mystery. While we can observe a sphere roughly 93 billion light-years in diameter, what lies beyond this particle horizon remains largely unknown, fueling a wealth of intriguing speculation. One possibility, of course, is that the universe extends infinitely beyond our observable region. If this is the case, then the structures and phenomena we observe within our cosmic horizon, galaxies, stars, and the cosmic web likely continue indefinitely, extending far beyond our current observational reach. This infinite expanse could potentially contain countless other galaxies, stars, and potentially even civilizations beyond our current ability to detect. Another possibility is that the universe, while not infinite, is far larger than our observable universe. This beyond might contain structures and regions that differ significantly from what we observe, perhaps with different physical laws or distributions of matter and energy. The uniformity of the observable universe, as suggested by the CMB, might not extend to these far-off regions, creating a universe vastly more complex than we currently imagine. Further adding to the mystery is the concept of the multiverse, the idea that our universe is just one among many, perhaps even infinitely many. These other universes could exist in separate regions of space-time, perhaps even with different physical laws or fundamental constants. Our universe in this view might be just one bubble in a much larger cosmic foam. Finally, we can't discount the possibility of unexpected phenomena beyond our observational limits. Perhaps forms of matter or energy that are currently unknown to us exist in these unseen regions, governed by laws of physics we haven't yet formulated. The universe beyond the horizon could hold surprises far beyond our current expectations, pushing the boundaries of scientific understanding. These are merely some of the myriad possibilities, all subject to ongoing scientific investigation and debate. The exploration of the universe beyond the horizon remains a compelling frontier of scientific endeavor. This leads us to another crucial aspect of modern cosmology, the accelerating expansion of the universe. Let's examine the implications of this discovery. For decades, astronomers assumed that the universe's expansion, first discovered by Edwin Hubble, was gradually slowing down. Gravity, after all, is an attractive force, and it seemed logical that it would eventually counteract the outward push of expansion. However, observations made in the late 1990s using distant supernovae as standard candles to measure cosmic distances revealed a stunning reality. The universe's expansion is not slowing down. It's accelerating. This unexpected discovery, which earned several scientists the Nobel Prize, introduced a new enigma into cosmology: dark energy. This mysterious force, seemingly permeating all of space, acts as a kind of anti-gravity pushing the universe apart at an ever-increasing rate. While we don't yet fully understand the nature of dark energy, its effects are profound and far-reaching. The accelerating expansion significantly alters our perspective on the universe's past, present, and future. It affects the observable universe's boundaries, creating the cosmic event horizon, a limit beyond which events can never affect us regardless of how long we wait. Galaxies beyond this horizon are receding from us faster than the speed of light, their light forever lost to our observation. The accelerating expansion also has implications for the universe's ultimate fate. While various scenarios are possible, the accelerating expansion suggests a universe that will continue to expand indefinitely, growing ever colder, darker, and emptier, a big freeze scenario. However, alternative models remain viable, highlighting the ongoing nature of scientific inquiry. The implications of the accelerating universe are not only cosmological, but fundamentally alter our grasp of time-space and the very future of the cosmos, reminding us of the immense scale and unresolved mysteries of the universe. This accelerating expansion further emphasizes the limitations inherent in our observations, leading us to consider the concept of the cosmic event horizon. Let's explore this profound boundary. The accelerating expansion of the universe driven by dark energy creates a profound and irreversible boundary, the cosmic event horizon. This isn't merely a limit on our current observational capabilities, like the particle horizon. It's a fundamental limit on what we can ever observe, a one-way street in spacetime. Imagine a galaxy far, far away. Light from that galaxy is traveling towards us, carrying information about its past. However, because the universe's expansion is accelerating, that galaxy is receding from us at an ever-increasing rate. Beyond a certain distance, the cosmic event horizon, the galaxy's recession speed surpasses the speed of light. This doesn't violate Einstein's theory of relativity, because it's not the galaxy itself moving faster than light through space. It's space itself stretching, carrying the galaxy beyond our observational reach. This means that light emitted from beyond the cosmic event horizon will never reach us. No matter how powerful our telescopes become, or how long we wait, those galaxies will remain forever hidden from view. This isn't just a matter of technological limitations. It's a fundamental constraint imposed by the physics of an accelerating universe. The cosmic event horizon represents an absolute boundary, a point of no return in our cosmic journey. The implications of the cosmic event horizon are profound. It challenges our understanding of causality, suggesting that events beyond this boundary can never have any influence on our observable universe. It also raises questions about the ultimate fate of the cosmos. In scenarios where the expansion continues to accelerate, increasingly larger portions of the universe will slip beyond our event horizon, ultimately leaving us isolated within a shrinking observable sphere. The cosmic event horizon is a stark reminder of the universe's immensity and the inherent limitations of our perspective within this vast and ever-expanding cosmos. It's a boundary not merely of distance, but of time and causality itself. This inherent limitation in our observations underscores the importance of understanding the constraints imposed by the speed of light and the age of the universe. Let's examine these fundamental limitations. Our ability to observe the universe is fundamentally constrained by two intertwined factors: the finite speed of light and the finite age of the universe. These limitations aren't merely technological hurdles. They represent inherent boundaries in our capacity to gather information about the cosmos. Light, the primary messenger from the universe, travels at a finite speed, approximately 299,792 kilometers per second. This means that when we observe a distant galaxy, we are not seeing it as it is now, but as it was when the light began its journey towards us. The farther away the galaxy, the further back in time we are looking. Observing distant galaxies is like looking into a cosmic history book with each photon carrying information from a specific moment in the past. The universe's age, estimated at around 13.8 billion years, further restricts our observational reach. This age sets a limit on how far back in time we can observe. Light from events that occurred before the universe's formation, of course, will never reach us. Even light from events immediately following the Big Bang wouldn't reach us until much later. Therefore, our view of the universe is not a snapshot of the present, but a limited glimpse into its past. This time constraint, coupled with the finite speed of light, means we can only observe a limited volume of space, our observable universe. Even if the universe itself is infinite, our view is necessarily confined by the age of the universe and the time it takes light to travel to us. Beyond the particle horizon lies the vast, largely unknown expanse of the cosmos, a testament to the scale and mystery of the universe, and a constant reminder that our knowledge remains, at least for now, incomplete. The limitations imposed by the speed of light and the age of the universe are inherent features of cosmology, not just technological limitations. This fundamental understanding shapes all of our approaches to cosmological inquiry. Given these constraints, it's crucial to acknowledge the assumptions underlying our cosmological models. Let's examine some of these foundational beliefs. Our cosmological models rely on several fundamental assumptions, simplifications, that allow us to build workable models of the universe's structure and evolution. Two of the most critical assumptions are uniformity and isotropy. These concepts, while seemingly straightforward, have profound implications for our understanding of the cosmos. Uniformity in this context refers to the idea that the universe is homogeneous, that is, its large-scale properties are roughly the same everywhere. Imagine a perfectly mixed bowl of soup. No matter where you take a spoonful, it will taste essentially the same. This is analogous to the assumption of uniformity in the universe. On sufficiently large scales, the distribution of matter and energy is relatively uniform throughout space. Isotropy, on the other hand, refers to the universe's appearance being the same in all directions. Imagine standing in the middle of a vast, flat plain. The view looks essentially the same, no matter which direction you look. This isotropy implies that the universe's large-scale properties are independent of direction. Observations of the cosmic microwave background, CMB, lend significant support to this assumption. The CMB's temperature is remarkably consistent across the sky, suggesting isotropy. These assumptions are not without their limitations. We only observe a limited region of the universe, our observable universe, which might not be representative of the entire cosmos. The universe might exhibit significant variations in density or properties beyond our current observational reach. Our models, therefore, are built on observations that may only be a local snapshot of a far larger, potentially far more heterogeneous reality. However, these assumptions, while ultimately extrapolations from our limited observations, provide a workable framework for understanding the universe on a large scale. They allow us to develop and test cosmological models, refine our understanding of the universe's evolution, and make predictions about its ultimate fate. It is crucial, however, to recognize that these are simplifying assumptions, and future observations may necessitate adjustments or refinements to our cosmological framework. The assumptions of uniformity and isotropy are fundamental to modern cosmology, but represent an ongoing area of scientific inquiry. Building upon these foundational assumptions, let's now turn our attention to Hubble's law and its implications for the expanding universe. This brings us to one of the cornerstones of modern cosmology. In the early 20th century, Edwin Hubble made a groundbreaking observation: distant galaxies are receding from us, and the farther away they are, the faster they're moving. This relationship, known as Hubble's law, provides compelling evidence for the universe's expansion. Hubble's law is expressed mathematically as V eintweisch h euro d, where v is the galaxy's recession velocity, d is its distance from us, and h0 is the Hubble constant, a proportionality constant that represents the universe's current expansion rate. The Hubble constant, while seemingly a simple number, is a subject of ongoing scientific debate, with different measurement methods yielding slightly different values. The discovery of Hubble's law wasn't simply a measurement, it was a paradigm shift in our understanding of the universe. Before Hubble's work, the universe was often considered static and unchanging. Hubble's law, however, provided strong evidence that the universe is not only expanding, but that this expansion has been ongoing since the Big Bang. It's important to note that Hubble's law doesn't describe galaxies moving through space. Rather, it describes the expansion of space itself. Imagine dots drawn on a balloon. As you inflate the balloon, the dots move farther apart, not because they're moving on the balloon's surface, but because the surface itself is expanding. This is analogous to the expansion of the universe. Galaxies are carried apart as the fabric of space stretches and expands. Hubble's law, therefore, is a cornerstone of modern cosmology, providing strong observational support for the Big Bang theory and shaping our understanding of the universe's dynamic nature and its ongoing evolution. This fundamental law continues to guide our exploration of the cosmos and the mysteries it holds. This understanding of expansion, in turn, leads us to consider the Hubble radius and its implications for our observational capabilities. Let's explore this crucial concept. Hubble's law, which describes the relationship between a galaxy's distance and its recession velocity, has a crucial implication for our ability to observe the universe, the Hubble radius. This radius defines a sphere around us beyond which galaxies are receding faster than the speed of light. This doesn't violate Einstein's theory of relativity, because it's not the galaxies themselves moving faster than light through space. It's space itself expanding, carrying galaxies beyond our observational reach. The Hubble radius is the distance at which this recession speed equals the speed of light. Beyond this radius, the light from galaxies can never reach us regardless of how long we wait. The Hubble radius isn't a fixed value. It's constantly changing as the universe's expansion rate evolves. The precise value depends on the Hubble constant, a number that represents the universe's current expansion rate, and is still being refined by astronomers through various measurement methods. However, current estimates place the Hubble radius at a considerable distance far beyond the currently observable universe. This means that even if the universe is not accelerating in its expansion, we would still have a fundamental limitation to how much we can see. The Hubble radius creates a practical limit on our observational capabilities, highlighting the ongoing tension between the universe's vastness and our ability to access information about it. The existence of the Hubble radius therefore underscores the limitations of our current understanding of the universe and the challenges we face when trying to unravel the mysteries of the cosmos. It's a boundary that reminds us of the ongoing quest to push the limits of our observational capabilities and understand the universe in all its immense scale and complexity. This leads us to consider the profound influence of dark energy on the universe's expansion. The discovery that the universe's expansion is accelerating rather than decelerating, as previously thought, introduced one of the most profound mysteries in modern cosmology: dark energy. This mysterious entity, comprising roughly 68% of the universe's total energy density, acts as a kind of cosmic repellent, counteracting gravity's attractive force and driving the accelerated expansion. While we don't yet have a complete understanding of dark energy's nature, its existence is strongly supported by observations of distant supernovae. These exploding stars serve as standard candles objects with a known intrinsic brightness allowing astronomers to measure distances across the vast expanse of the universe. Observations of these distant supernovae revealed that their apparent dimness indicated a faster-than-expected rate of expansion, suggesting the presence of a repulsive force accelerating the universe's expansion. The implications of dark energy are far-reaching. It profoundly affects our understanding of the universe's large-scale structure, its ultimate fate, and the very nature of gravity. The accelerating expansion driven by dark energy is responsible for the creation of the cosmic event horizon, a boundary beyond which galaxies are receding faster than the speed of light, their light forever inaccessible to us. Dark energy's influence also has significant implications for the universe's ultimate fate. The most widely accepted model suggests a Big Freeze scenario, where the universe continues to expand indefinitely, eventually reaching a state of maximum entropy, a cold, dark, and lifeless expanse. However, alternative models involving a potential Big Rip or even a cyclical universe remain within the realm of possibility. Dark energy, therefore, is not merely a theoretical construct. It's a crucial component of our cosmological models reflecting the universe's mysterious nature. While its precise nature remains an open question, its profound impact on the universe's expansion is undeniable, shaping our understanding of the cosmos on the grandest of scales and pointing towards an even greater depth of unanswered questions yet to be explored. This accelerating expansion has a direct and observable consequence: the gradual fading of distant galaxies. Let's explore this phenomenon. The accelerating expansion of the universe driven by dark energy has a direct and observable consequence: the gradual fading of distant galaxies. This isn't a sudden disappearance. It's a slow, inexorable process, stretching over billions of years, as the universe's expansion stretches and redshifts the light from these receding galaxies. Imagine a distant galaxy emitting light towards us. As this light travels across the vast expanse of space, the universe continues to expand. This expansion stretches the light waves, increasing their wavelength and shifting them towards the red end of the electromagnetic spectrum, a phenomenon known as redshift. The more distant the galaxy, and the longer the light has been traveling, the greater the redshift. This redshifting has several observable effects. Firstly, the light from distant galaxies becomes progressively dimmer as its energy is spread across a larger wavelength. Secondly, the light shifts from visible wavelengths into infrared and eventually radio wavelengths, moving beyond the range of our optical telescopes. Dedicated infrared telescopes like the James Webb Space Telescope are crucial for observing these red-shifted galaxies. As the universe continues to expand and accelerate, this fading process will continue making increasingly larger portions of the universe unobservable. Galaxies that are currently visible will gradually fade from view, their light stretched and weakened beyond our detection capabilities. This cosmic fading is not just a limitation of our technology, it's an inherent consequence of the universe's accelerating expansion. This gradual disappearance of galaxies underscores the dynamic and ever-changing nature of our observable universe and the profound impact of dark energy on the cosmic landscape. It's a humbling reminder of the vastness and the constantly evolving nature of the cosmos, pushing the boundaries of our understanding and inspiring further exploration. This fading, however, presents significant challenges for astronomers. Observing extremely distant objects presents astronomers with a multitude of significant challenges. These challenges aren't merely technological limitations, they are fundamental obstacles rooted in the very nature of light distance and the expanding universe. The most immediate challenge is the faintness of the signal. Light from distant galaxies travels billions of years to reach us, its energy spread thinly across an ever-expanding volume of space. By the time this light reaches our telescopes, it's incredibly faint, often requiring long exposure times and highly sensitive detectors to capture a meaningful signal. This faintness is exacerbated by the redshifting of light due to the universe's expansion. As light travels across expanding space, its wavelength stretches, shifting it towards the red end of the spectrum and reducing its energy further. Another challenge stems from the limitations of our telescopes. Even the most powerful telescopes have a finite aperture, a limited light-gathering capacity. This limits the faintest signals they can detect, effectively placing an observational boundary beyond which certain objects remain invisible. Furthermore, the Earth's atmosphere can scatter and absorb light, further reducing the clarity and intensity of distant signals. This atmospheric interference necessitates the use of space-based telescopes, like the Hubble Space Telescope and the James Webb Space Telescope, which operate above the distorting effects of the atmosphere. Moreover, the sheer number of celestial objects in the universe presents an additional challenge. Distinguishing the light from a particular distant galaxy from the light of other galaxies and stars requires highly sophisticated techniques and advanced image processing. The density of objects in certain regions of space further complicates observation, particularly at high redshift, where the objects appear as tiny, faint points of light. Finally, the accelerating expansion of the universe pushes galaxies beyond our reach, creating the cosmic event horizon, a boundary beyond which light can never reach us. Observing deep space, therefore, is not just a technological challenge, but a fundamental race against time and distance, highlighting the immense scale and ongoing mysteries of the cosmos. Despite these challenges, astronomers continue to push the boundaries of observation, seeking to detect and study the oldest light in the universe. This brings us to the fascinating quest to detect and analyze the oldest light we can observe. The quest to observe the oldest light in the universe is a testament to human ingenuity and our relentless pursuit of knowledge. This light, the cosmic microwave background, CMB, is a relic from the early universe, a faint echo of the Big Bang itself. Detecting and studying this ancient radiation requires specialized instruments and sophisticated techniques. The CMB's photons emitted roughly 380,000 years after the Big Bang have been traveling through space ever since. However, the universe's subsequent expansion has stretched their wavelengths, shifting them from visible light into the microwave portion of the electromagnetic spectrum. This redshifting makes the CMB invisible to the naked eye and requires specialized radio telescopes and detectors to observe. Early observations of the CMB were made using ground-based radio telescopes, but these were hampered by atmospheric interference. Subsequently dedicated space-based missions such as the Cosmic Background Explorer, COBE, the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite provided far more precise and detailed measurements. These missions mapped the CMB's minute temperature variations across the sky, revealing the seeds of the large-scale structures we see in the universe today. The James Webb Space Telescope, while primarily designed for infrared observations of distant galaxies, also contributes valuable data related to the CMB. Its unprecedented sensitivity allows for the detection of incredibly faint signals, pushing the boundaries of our understanding of the early universe. By analyzing the CMB's minute temperature fluctuations, scientists can extract a wealth of information about the universe's composition, geometry, and expansion history. This ancient light therefore acts as a cosmic time capsule, providing a direct link to the universe's infancy and serving as a cornerstone of our cosmological models. The study of the CMB continues to be a critical area of research, pushing the boundaries of our understanding of the universe's origins and evolution. However, even this oldest light has its limitations in revealing the universe's earliest moments. The universe's expansion stretches the light waves traveling through it, causing a phenomenon known as redshift. This redshift is analogous to the Doppler effect you hear when a siren approaches and then recedes. As the source of sound moves closer, the sound waves compress, resulting in a higher pitch. As it moves away, the waves stretch, resulting in a lower pitch. Similarly, as galaxies move away from us due to the universe's expansion, the light waves they emit stretch, shifting them toward the red end of the electromagnetic spectrum. The amount of redshift is directly related to the galaxy's distance and recession velocity. The greater the distance and the faster the galaxy is moving away from us, the more the light waves are stretched and the greater the redshift. This relationship, combined with our understanding of the universe's expansion rate, the Hubble constant, allows astronomers to measure the distances to incredibly faraway galaxies. Redshift is a crucial tool in cosmology, enabling us to map the distribution of galaxies across the vast expanse of the universe. By measuring a galaxy's redshift, astronomers can estimate its distance and, by extension, its recession velocity. This information allows us to study the large-scale structure of the universe, mapping the distribution of galaxies, galaxy clusters, and voids. The redshift of light from the most distant galaxies also provides crucial information about the early universe, allowing us to trace its evolution from the Big Bang. However, it's important to note that redshift measurements alone don't provide a direct measurement of distance. The relationship between redshift and distance is complex, influenced by factors like the universe's expansion rate and geometry. To accurately measure distances, astronomers often use multiple methods to calibrate and confirm their estimations. Despite these complexities, redshift remains a vital tool in our quest to understand the universe's structure and history, a critical aspect of the cosmic distance ladder. This ongoing refinement of measurement methods highlights the dynamic nature of scientific exploration and understanding of the universe's vast expanse. This brings us to a discussion of the James Webb Space Telescope and its groundbreaking contributions to our understanding of the early universe. Let's explore its capabilities and discoveries. Launched in late 2021, the James Webb Space Telescope (JWST) represents a monumental leap forward in our ability to observe the universe. Its unprecedented infrared capabilities allow it to peer deeper into space and further back in time than ever before, providing invaluable insights into the early universe's formation and evolution. Unlike its predecessor, the Hubble Space Telescope, which primarily observes visible light, the JWST is optimized for infrared wavelengths. This is crucial because the expansion of the universe stretches the light from distant objects, shifting it from visible wavelengths into the infrared. The JWST's sensitivity to infrared light allows it to detect the faint red-shifted light from the earliest galaxies, revealing details about their structure composition and formation processes. In its first year of operation alone, JWST has already made groundbreaking discoveries, including the detection of several candidate galaxies with redshifts above 10, meaning their light has been traveling for over 13 billion years. These galaxies, some potentially formed just 300 million years after the Big Bang, offer a unique window into the universe's earliest stages of star and galaxy formation. Their properties, including their unexpectedly high luminosity and apparent maturity, challenge existing models of early cosmic evolution. The JWST's observations aren't limited to distant galaxies. It also provides data relevant to the cosmic microwave background (CMB), offering new perspectives on the universe's initial conditions. Its advanced instruments allow for incredibly precise measurements, furthering our understanding of the universe's composition, expansion rate, and underlying physical processes. The JWST, therefore, is not just a telescope. It's a powerful tool for unraveling the universe's deepest mysteries, providing unprecedented insights into the earliest moments of cosmic history. Its observations are constantly refining our cosmological models and fueling a new era of discovery, deepening our understanding of the universe's evolution and challenging our existing assumptions about its origins. This improved observational capability allows us to explore the formation of the earliest galaxies. The formation of the earliest galaxies remains one of the most compelling mysteries in modern cosmology. These first galaxies, emerging from the relatively uniform distribution of matter in the early universe, represent the initial steps in the universe's complex structure formation. Understanding their formation requires piecing together evidence from various sources, including observations of distant galaxies, theoretical models, and simulations. The universe's early stages were characterized by a relatively uniform distribution of matter, with only tiny density fluctuations, as revealed by the cosmic microwave background (CMB), providing the seeds for future structure. These tiny variations, amplified by gravity, over time led to the gradual clustering of matter, eventually forming the first stars and galaxies. The process of galaxy formation is complex and involves a multitude of interacting factors, including gravity, dark matter, gas dynamics, and feedback from stars. Dark matter, a mysterious substance that doesn't interact with light but exerts gravitational influence, plays a crucial role providing the gravitational scaffolding upon which galaxies are built. Gas clouds, initially dispersed throughout space, are drawn together by the gravity of dark matter, halos eventually collapsing under their own gravity to form stars. The first stars were likely much more massive than those we see today, burning through their fuel rapidly and exploding as supernovae. These explosions enriched the surrounding gas clouds with heavier elements, providing the building blocks for future generations of stars and planets. Over time, these stars and gas clouds clustered together, forming increasingly larger structures, ultimately leading to the formation of the galaxies we observe today. The James Webb Space Telescope, JWST, with its exceptional infrared capabilities, is providing unprecedented insights into the formation of these early galaxies. Its observations are revealing details about the structure, composition, and formation processes of galaxies at extremely high redshifts, pushing the boundaries of our understanding of the universe's early stages of cosmic evolution. The study of early galaxy formation is an active and evolving area of research, constantly refined by new observations and theoretical models. Unraveling the mysteries of these first galaxies is a key goal in our ongoing quest to understand the universe's history and its ultimate destiny. Analyzing the light from these ancient galaxies provides crucial clues about the universe's early conditions. Let's explore what this ancient starlight can reveal. The light from distant galaxies, red-shifted by the universe's expansion, carries with it a wealth of information about the universe's early conditions. This ancient starlight, painstakingly collected and analyzed by astronomers, provides crucial clues about the properties and evolution of the earliest galaxies. By studying the spectrum of light emitted by these distant galaxies, astronomers can determine their composition. The presence of specific elements and molecules in a galaxy's spectrum reveals details about the types of stars it contains, its gas content, and its overall chemical makeup. For example, the abundance of heavier elements beyond hydrogen and helium, indicates the history of star formation within the galaxy. Heavier elements are forged in the cores of stars and released into space when stars explode as supernovae. A higher abundance of heavier elements implies a history of significant star formation. The brightness of a galaxy's light provides further clues. The apparent brightness combined with redshift measurements helps astronomers estimate a galaxy's intrinsic luminosity, its true energy output. This in turn provides information about the galaxy's size, star formation rate, and overall energy budget. The shape and distribution of light within a galaxy also hold clues about its structure, revealing whether it is a spiral galaxy, an elliptical galaxy, or an irregular galaxy. The detailed analysis of these factors enables astronomers to construct a picture of the galaxy's history. The James Webb Space Telescope JWST, with its unprecedented infrared sensitivity, is dramatically enhancing our ability to study the light from these ancient galaxies. Its observations are providing increasingly detailed insights into the physical properties and evolutionary paths of these early galaxies. This information, in turn, is refining our understanding of galaxy formation, the universe's expansion history, and the overall evolution of the cosmos. Studying this ancient starlight therefore provides a powerful means to probe the universe's distant past, revealing the secrets held within the light itself. However, even with these advanced techniques, observing the very earliest moments of the universe presents significant challenges. Let's examine these limitations. Even with advancements in telescope technology, observing the very early universe presents formidable challenges. These challenges aren't simply technological limitations, but are inherent to the nature of light time and the universe's expansion. The primary obstacle is the immense distance involved. The light from the earliest structures has traveled billions of light years to reach us, resulting in an extremely faint and red-shifted signal. This faintness requires extremely long exposure times and highly sensitive detectors to gather enough photons for meaningful analysis, pushing the limits of our current technology. Another significant hurdle is the red-shifting of light. As light travels through the expanding universe, its wavelength stretches, shifting it toward the red end of the electromagnetic spectrum. This redshift not only dims the light, but also shifts it out of the visible range for many wavelengths, necessitating infrared and radio telescopes to detect the faint signals emitted by early galaxies. Furthermore, the early universe was dense and opaque. Before recombination, the epoch when the universe cooled enough for neutral atoms to form the universe was a hot, ionized plasma that scattered light, preventing photons from traveling freely. This means we can only directly observe the universe after recombination, when light could finally decouple from matter. Thus, our view of the early universe is naturally limited to the time after recombination, leaving the universe's earliest moments shrouded in mystery. Finally, the accelerating expansion of the universe driven by dark energy further complicates our observations. The universe's accelerated expansion is pushing galaxies beyond our reach, creating the cosmic event horizon, a boundary beyond which light will never reach us, irrespective of technological advances. The study of the early universe, therefore, is not just a race against technological limitations, but a race against the very expansion of space-time, constantly pushing the boundaries of our knowledge and our capacity to explore the universe's origins. These limitations, however, don't diminish the importance of studying the cosmic microwave background. Let's examine its limitations and the search for signals beyond it. The cosmic microwave background. CMB, while providing invaluable insights into the early universe, also presents a fundamental observational limit. This ancient light, emitted roughly 380,000 years after the Big Bang, represents the furthest back in time we can directly observe using electromagnetic radiation. Before this epoch, the universe was a dense, hot plasma opaque to light. Photons couldn't travel freely. They constantly scattered off charged particles, preventing the formation of a clear image. The CMB therefore acts as a kind of cosmic curtain, obscuring our direct view of the universe's earliest moments. While the CMB itself carries information about the conditions of the early universe, its temperature, density, and composition, it doesn't provide a direct image of events that occurred. before recombination, when the universe became transparent to light. This limitation is not a technological constraint, but an inherent feature of the universe's early evolution. This limitation, however, doesn't imply that we can learn nothing about the period before recombination. Theoretical models informed by our understanding of physics and the CMB's properties allow us to make inferences about the very early universe. These models, however, involve significant uncertainties and rely on extrapolations from what we can observe. Moreover, other potential signals, such as gravitational waves, might offer alternative pathways to studying this period. The CMB's observational limits therefore highlight the challenges and opportunities inherent in exploring the universe's earliest moments. While the CMB offers a remarkable window into the early universe, it also underscores the limitations of relying solely on electromagnetic radiation to study this era. This leads us naturally to consider other potential messengers from the cosmos's early moments, pushing the boundaries of our observational capabilities and expanding our understanding of the universe's very beginnings. This motivates a search for other potential signals from beyond the CMB. The cosmic microwave background. CMB, while offering a remarkable glimpse into the early universe, represents a limit to our observations based on electromagnetic radiation. However, the universe may hold secrets beyond the CMB's reach, requiring us to explore other potential messengers from the cosmos's earliest moments. One promising avenue of investigation involves gravitational waves. Unlike light, which can be scattered and absorbed by matter, gravitational waves can travel unimpeded through the universe, carrying information from the very early universe. While detecting these faint ripples in spacetime is an immense technological challenge, ongoing experiments, like BICEP, aim to detect these elusive signals, potentially offering a window into the universe's earliest moments before the CMB formed. Another potential source of information lies in neutrinos. These elusive subatomic particles, far less massive and interactive than photons, could have traveled unimpeded from the very early universe. Detecting these neutrinos, however, presents exceptional challenges. They interact so weakly with matter that capturing sufficient numbers requires extremely large detectors and advanced techniques. Despite this difficulty, researchers are actively pursuing methods to detect these early universe neutrinos, potentially unveiling new information about the Big Bang and its immediate aftermath. Additionally, some theoretical models suggest the possibility of other, as yet undiscovered particles or fields that might have left detectable imprints. These hypothetical particles could have interacted with the universe in ways that left unique signatures in the cosmic background radiation or in the large-scale structure of the universe. The search for such signals, therefore, remains an active area of research, constantly pushing the boundaries of our understanding and our capacity to explore the universe's most fundamental constituents. The quest to detect these signals, whether gravitational waves, neutrinos, or other currently unknown phenomena, pushes the boundaries of what's possible in our search to unravel the very fabric of reality, offering a tantalizing glimpse into epochs hidden behind the CMB's cosmic curtain. These messengers from the early universe, however, are incredibly faint and challenging to detect. While the cosmic microwave background, CMB, provides a remarkable snapshot of the universe, at around 380,000 years after the Big Bang, it offers limited information about the universe's earliest moments. Gravitational waves, however, offer a potentially powerful tool for probing this previously inaccessible era. Predicted by Albert Einstein's theory of general relativity, gravitational waves are ripples in the fabric of spacetime, generated by some of the universe's most energetic events, such as the collision of black holes or neutron stars. Unlike light, which can be scattered and absorbed by matter, Gravitational waves can travel unimpeded through the universe, carrying information from its earliest moments. Detecting these faint ripples in space-time presents immense technological challenges. The signals are incredibly weak, requiring highly sensitive detectors shielded from terrestrial and cosmic noise. Ground-based detectors, such as LIGO and Virgo, have successfully detected gravitational waves from relatively recent events, like black hole mergers. However, detecting gravitational waves from the early universe waves that have traveled across the vast expanse of space for billions of years requires even greater sensitivity and innovative detection strategies. Experiments like BICEP, which search for a faint polarization pattern in the CMB, aim to detect primordial gravitational waves, waves generated during the universe's earliest moments, potentially during the epoch of inflation. Detecting these primordial waves would provide invaluable insights into the universe's very first moments, providing information about the conditions that existed before the CMB formed. The detection of primordial gravitational waves would represent a landmark achievement in cosmology, offering a unique and powerful way to test our understanding of the universe's very origins and its subsequent evolution. The study of gravitational waves, therefore, is a frontier of research that holds the key to unlocking some of the deepest mysteries of the cosmos, offering a window into a previously unseen era. However, detecting these faint signals presents significant challenges. The quest to detect faint signals from the early universe presents a formidable set of challenges. These aren't simply technological limitations. They stem from the fundamental properties of the universe itself, the vast distances involved, and the inherent weakness of these ancient signals. The most significant hurdle is the sheer faintness of the signals. Photons from the early universe have been traveling for billions of years, their energy spread thinly across an ever-expanding volume of space. By the time they reach us, these signals are incredibly weak, often buried beneath a cacophony of foreground noise from our own galaxy and other celestial sources. This necessitates extremely sensitive detectors and sophisticated data analysis techniques to extract meaningful information from the noise. Another significant challenge is the red-shifting of these signals. The universe's expansion stretches the wavelengths of light, shifting it towards the red end of the spectrum. This redshifting not only reduces the signal's energy, but also moves many wavelengths beyond the range of optical telescopes, requiring specialized infrared and radio telescopes for detection. Moreover, this redshifting makes it difficult to distinguish the faint signals from the early universe from other sources of radiation at similar wavelengths. Furthermore, disentangling the desired signals from the noise requires advanced data analysis techniques. Subtracting foreground noise and separating the faint signals from other sources demands sophisticated algorithms and meticulous calibration. The complexity of this data analysis is considerable, necessitating specialized expertise and significant computational resources. Finally, the accelerating expansion of the universe, driven by dark energy, pushes the boundaries of observability even further. The cosmic event horizon represents the ultimate limit to our observational capabilities. Signals from beyond this boundary will never reach us. Detecting faint signals from the early universe, therefore, is not simply a technical challenge, but a fundamental race against both time and distance, highlighting the immense scale and complexity of the cosmos. The pursuit of this knowledge requires persistent innovation and ingenuity in observational techniques and data analysis. This brings us to a discussion of cosmic inflation, a pivotal moment in the universe's early history. Let's explore this rapid expansion and its consequences. The Big Bang Theory describes the universe's expansion from an incredibly hot, dense state. However, this theory alone doesn't fully explain certain observed features of the universe, such as its remarkable uniformity and flatness. To address these puzzles, cosmologists have proposed a period of extremely rapid expansion in the very early universe known as cosmic inflation. Imagine inflating a balloon incredibly quickly. In a fraction of a second, a tiny speck expands to a size far larger than its initial dimensions. This rapid expansion smooths out any initial irregularities on the balloon's surface. Cosmic inflation functions similarly, proposing a period of exponential expansion in the very early universe, occurring within a tiny fraction of a second after the Big Bang. During inflation, the universe's size increased exponentially, smoothing out any initial density fluctuations. This rapid expansion explains the remarkable uniformity of the cosmic microwave background (CMB), the afterglow of the Big Bang observed across the entire sky. Without inflation, different regions of the sky would have been causally disconnected, preventing the observed uniformity in temperature. Moreover, inflation helps explain the universe's flatness. The universe's geometry can be flat spherical or hyperbolic, depending on the density of matter and energy. A flat universe represents a precise balance between these two forces. While a flat universe isn't impossible without inflation, inflation provides a mechanism to explain why the universe appears to be so remarkably flat, even at its earliest stages. While cosmic inflation is a highly successful theoretical model, it remains a hypothesis that hasn't been directly observed. However, ongoing experiments are actively searching for evidence of primordial gravitational waves, ripples in spacetime produced during the inflationary epoch. The detection of these waves would provide strong observational support for the inflation theory. The study of cosmic inflation, therefore, is a central area of investigation in modern cosmology, offering a potential solution to several puzzles associated with the universe's earliest moments and shaping our understanding of how the universe evolved into the complex structure we observe today. The evidence for inflation is strong, but proving its occurrence remains a significant challenge. This rapid expansion, however, has significant implications for our ability to observe the universe. Let's explore these consequences. The remarkable uniformity of the cosmic microwave background, CMB, the afterglow of the Big Bang, provides compelling support for the theory of cosmic inflation. The CMB's temperature is remarkably consistent across the entire sky, with only tiny variations, a few parts per 100,000, indicating a universe that was once incredibly uniform in its early stages. This uniformity, however, presents a significant puzzle. Without a period of rapid expansion, like inflation, different regions of the sky would have been causally disconnected in the early universe. In other words, information couldn't have traveled fast enough between these regions to create the observed uniformity. The speed of light, while remarkably fast, is not infinite. The universe's expansion itself places fundamental limitations on how much information can be exchanged across great distances, particularly in the early universe, when the universe was smaller and denser. However, the theory of cosmic inflation elegantly addresses this challenge. During inflation, the universe underwent an incredibly rapid expansion, exponentially increasing in size within a tiny fraction of a second after the Big Bang. This rapid expansion stretched the universe, smoothing out any initial density variations. Imagine stretching a crumpled piece of paper. The wrinkles smooth out as the paper is stretched. Similarly, inflation smoothed out the early universe's density fluctuations, resulting in the remarkably uniform temperature distribution we observe in the CMB today. The observed uniformity of the CMB therefore provides strong, albeit indirect, support for the theory of inflation. While we haven't directly observed inflation, the CMB's uniformity is difficult to explain without invoking a period of rapid exponential expansion in the very early universe. This doesn't prove inflation definitively, but it provides compelling evidence in favor of this remarkable theory, a theory that helps us understand why the universe is so uniform and flat, despite the limitations imposed by the finite speed of light and the expansion of space. The uniformity of the CMB therefore stands as a key pillar supporting the theory of cosmic inflation, highlighting the interconnectedness of the universe's seemingly disparate aspects and the remarkable consistency of our observations with the predictions of this theory. This period of rapid expansion, however, also has important implications for our ability to observe the universe. Let's explore these observational consequences. The theory of cosmic inflation, while explaining several key features of the universe, also profoundly impacts our ability to observe it. This rapid expansion in the very early universe has created a boundary beyond which we cannot see a limit, not just of current technology, but of fundamental physics. During inflation, the universe expanded exponentially, stretching the fabric of space-time itself. This expansion far exceeding the speed of light, though not violating relativity, as its space itself expanding effectively, pushed regions of space beyond our observational reach. Imagine a balloon with dots representing galaxies. As you inflate the balloon rapidly, some dots move so quickly that they are pushed beyond your field of vision, regardless of how fast you try to follow them. This effect creates a horizon problem, similar to the particle horizon we discussed earlier, but with a far more profound implication. This horizon isn't defined simply by the speed of light and the universe's age. It's rooted in the physics of inflation itself. Regions of space that were initially close enough to interact before inflation, exchanging information through the exchange of light and particles, were subsequently stretched so far apart that they are now causally disconnected, a consequence of the expansion greatly exceeding the speed of light. Their light will never reach us. This inflationary horizon isn't merely a limit to our current technology. It's a fundamental limit on the information we can ever access about the universe. It represents a boundary imposed by the physics of inflation and the expansion of space, highlighting the challenges inherent in our quest to understand the universe's earliest moments. While the CMB offers a glimpse into this early universe, the inflationary horizon acts as a barrier, preventing us from seeing what might have transpired in regions beyond the reach of the currently observable universe. This inherent limitation underscores the dynamic and ever-evolving nature of our cosmic horizon. Therefore, our explorations into the very early universe are not only constrained by the age of the universe and the speed of light, but also by the physics of inflation itself. This fundamental limitation sets a profound boundary on what we can know and understand about the cosmos. This concept of an unreachable region naturally leads us to consider the theory of eternal inflation and its implications for a multiverse. Let's explore this fascinating and highly speculative idea. The theory of cosmic inflation, while remarkably successful in explaining several key features of the universe, leads to a mind-bending extension, eternal inflation. This theory proposes that inflation didn't end everywhere at once, but continues indefinitely in some regions of space-time, creating a vast, potentially infinite multiverse. Imagine a boiling pot of water. Bubbles constantly form, expand, and then pop. Eternal inflation envisions something similar, but on a cosmic scale. Space-time itself is undergoing continuous inflation with new, bubble universes constantly forming, each undergoing its own period of inflation and potentially evolving into distinct realities. Our own universe in this model is just one of these bubbles, a single isolated region within a much larger, possibly infinite multiverse. Each bubble universe in this scenario could have different physical laws, fundamental constants, and even different numbers of spatial dimensions. The properties of each bubble universe are determined by the specific conditions that prevailed when that bubble formed from the inflating background. This leads to the intriguing possibility of a vast ensemble of universes, each with its own unique characteristics, a concept often referred to as the inflationary multiverse. The implications of eternal inflation are profound and highly speculative. The sheer scale and diversity of this multiverse are staggering, potentially encompassing every conceivable reality. This raises profound philosophical questions about our own universe's place within this vast ensemble, the nature of reality itself, and the possibility of other life forms. It's crucial to emphasize that eternal inflation remains a theoretical concept, largely untestable with our current technology. However, it represents a compelling extension of our understanding of inflation, highlighting the potential for an infinitely larger and more diverse cosmos than we can currently observe. While the evidence for inflation is strong, the concept of eternal inflation pushes the boundaries of our imagination and our capacity to comprehend the true scale and nature of reality. The possibility of a multiverse born from the never-ending process of eternal inflation remains one of the most tantalizing and challenging ideas in modern cosmology. This leads us to a broader discussion of multiverse theories. The concept of a multiverse. The idea that our universe is just one among many is a captivating and highly speculative area of modern cosmology and physics. While not yet directly testable, multiverse theories arise from several different lines of reasoning, each suggesting the potential existence of other universes beyond our own. One prominent multiverse model stems from the theory of eternal inflation. As discussed earlier, eternal inflation proposes that the inflationary epoch of the Big Bang never truly ended, resulting in the continuous creation of new bubble universes, each with potentially different physical laws and constants. Our universe in this scenario would be just one bubble in a vast, possibly infinite sea of other universes. Another class of multiverse theories arises from the many worlds interpretation of quantum mechanics. This interpretation suggests that every quantum measurement causes the universe to split into multiple branches, each representing a different possible outcome. Each branch in this view constitutes a separate universe, leading to a vast, constantly branching multiverse. String theory. A framework attempting to unify all fundamental forces also suggests the possibility of a multiverse. String theory proposes that our four-dimensional universe, 3 spatial dimensions plus time, is embedded within a higher dimensional space, potentially containing numerous other universes with different properties. These universes might be separated by extra spatial dimensions inaccessible to us, existing as separate branes within this higher dimensional space. Finally, the concept of a mathematical multiverse suggests that all mathematically consistent universes exist, making our own universe just one realization among many potential realities. This idea pushes the boundaries of physics, blending mathematical possibility with physical existence. It's crucial to acknowledge that multiverse theories are highly speculative and currently untestable. However, these concepts arise from established frameworks within physics and cosmology, suggesting the potential for a reality far grander and more complex than our observable universe. The exploration of these ideas continues to be a compelling endeavor, pushing the limits of our understanding and inspiring further investigation into the nature of reality itself. The very idea of a multiverse challenges our understanding of existence, potentially revolutionizing our place in the cosmos. Let's delve deeper into one specific model, the inflationary multiverse. The inflationary multiverse, a concept arising from the theory of eternal inflation, presents a breathtakingly vast and complex picture of reality. It proposes that our universe is just one of countless others, each potentially with different physical laws, fundamental constants, and even different numbers of spatial dimensions. Eternal inflation suggests that the inflationary epoch that characterized the very early universe didn't end everywhere at once. Instead, some regions of spacetime continue to undergo inflation indefinitely, constantly creating new bubble universes. Imagine a boiling pot of water with bubbles constantly forming, expanding, and then popping. Eternal inflation envisions something similar, but on a cosmic scale, with our universe being just one of these bubbles. Each bubble universe arises from a fluctuation within the inflating background, a region of spacetime undergoing eternal inflation. The properties of each bubble, its physical laws, fundamental constants, and even its dimensionality are determined by the specific conditions that prevailed when that bubble formed. This leads to the potential for an incredibly diverse multiverse, encompassing an almost limitless range of possible realities. Within the inflationary multiverse, some bubble universes might be similar to our own, while others might be radically different. Some might be devoid of matter, while others might contain exotic forms of matter and energy that are currently unknown to us. The laws of physics themselves could vary dramatically between these bubble universes, leading to fundamentally different realities. It's important to remember that the inflationary multiverse remains a highly speculative theory. We have no direct observational evidence of other universes, and the theory's testability is currently highly limited. Nevertheless, the inflationary multiverse provides a compelling framework for understanding the potential vastness and diversity of the cosmos, a framework that arises naturally from well-established theories of physics. Exploring this concept expands our understanding of what's possible and pushes the boundaries of our imaginations. The very idea challenges our concepts of existence, uniqueness, and our place within the grand scheme of reality. It serves as a testament to both the immense scope of the cosmos and the power of theoretical physics to probe the deepest mysteries of existence. This diversity of potential universes raises intriguing questions about their individual properties. Let's explore some of these possibilities. The concept of a multiverse, particularly the inflationary multiverse, opens up a vast landscape of possibilities. If our universe is just one among many, then those other universes could possess vastly different properties compared to our own. Let's explore some of these intriguing possibilities. One key difference could lie in the fundamental constants of nature. In our universe, the values of these constants, such as the gravitational constant, the speed of light, and the Planck constant, are precisely tuned to allow for the formation of stars, galaxies, and ultimately life as we know it. However, in other universes, these constants could have different values, potentially leading to dramatically different physical laws and cosmic structures. Imagine a universe where the gravitational constant is significantly stronger. In such a universe, stars might be smaller and burn out much more quickly. Galaxies might be denser and more compact, or perhaps even prevented from forming altogether. Alternatively, a universe with a weaker gravitational constant could lead to the formation of vastly larger structures, or even prevent the formation of stars entirely. The very fabric of space-time itself could be fundamentally different. The number of spatial dimensions could also vary between universes. Our universe has 3 spatial dimensions, but some theories suggest that other universes could have more or fewer dimensions. A universe with more dimensions could have vastly different geometries and physical laws, potentially leading to forms of matter and energy entirely unlike anything we can currently conceive. Conversely, a 2-dimensional universe would have fundamentally different physical properties and would likely be governed by different laws. Furthermore, the fundamental forces of nature could differ between universes. In our universe, we have 4 fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. However, other universes might have different forces or combinations of forces possibly leading to radically different forms of matter and energy. These differences could result in universes with vastly different structures and properties. The very concept of elements or even atoms might not exist. The possibilities are truly limitless, highlighting the vastness of the multiverse concept and the immense potential for diversity beyond our current understanding. Even speculation, however, requires a solid grounding in our current scientific understanding. These potential properties underscore the remarkable complexity and mystery of the cosmos. This diversity of potential universes, however, raises profound questions about the fine-tuning of physical constants. Let's explore this concept in the context of the multiverse. The universe's fundamental constants, such as the gravitational constant, the speed of light, and the fine structure constant, appear remarkably fine-tuned for the emergence of life as we know it. Slight alterations in these constants could have dramatically altered the universe's evolution, potentially preventing the formation of stars, galaxies, or even stable atoms. This apparent fine-tuning has led some to question whether it's merely a cosmic coincidence or a deeper reflection of the universe's underlying structure. The multiverse hypothesis offers a compelling perspective on this fine-tuning. If our universe is just one among many, each with potentially different physical constants, then it's not surprising that at least one universe would have the right conditions for life. It's like buying lottery tickets. The odds of winning are low for any individual ticket, but with enough tickets, it's statistically likely that someone will eventually win. Similarly, if countless universes exist, each with different physical constants, then at least one will inevitably have the precise combination of values necessary for life to emerge. In the inflationary multiverse model, for example, each bubble universe emerges with potentially different physical constants, determined by the specific conditions that prevailed during its formation from the inflating background. This leads to a vast ensemble of universes, each with its own unique set of physical laws. Some of these universes might be barren and lifeless, while others might harbor conditions suitable for life, perhaps even life forms far beyond our comprehension. This perspective shifts the focus from why our universe's constants are so precisely tuned to why we happen to exist within a universe with those specific values. We are, in essence, observing a universe where life is possible, because we wouldn't be here to observe otherwise. This doesn't diminish the remarkable fine-tuning. Rather, it suggests a possible explanation within a broader cosmological framework, a framework that transcends the limitations of a single universe and opens up the possibility of a far greater, more diverse, and perhaps even infinite cosmos. The fine-tuning, therefore, might not be a coincidence, but a consequence of the multiverse's immense diversity, highlighting the remarkable connection between the fundamental laws of physics and the existence of life itself. The implications of this hypothesis challenge our understanding of causality, probability, and the very nature of reality. However, testing these multiverse theories presents formidable challenges. Testing the existence of a multiverse presents a formidable challenge to scientists. By definition, other universes, if they exist, lie beyond our observational horizon, a barrier imposed by the physics of our own universe, not just a technological limitation. This makes direct observation of other universes currently impossible. However, this doesn't mean that multiverse theories are entirely untestable. Several approaches are being explored, each attempting to find indirect evidence that could support or refute the existence of a multiverse. One approach focuses on subtle anomalies within our own universe. Some theories predict that interactions between our universe and other universes, or between different regions within a multiverse, could leave detectable imprints in the cosmic microwave background, CMB, or in the large-scale structure of the universe. Careful analysis of the CMB and galaxy distribution is crucial in this endeavor. Another approach involves searching for variations in fundamental constants. If our universe is just one among many, each with potentially different fundamental constants, then it's possible to detect variations in these constants across different regions of space or at different epochs in the universe's history. This search relies on highly precise measurements and rigorous statistical analysis to distinguish genuine variations from observational uncertainties. Furthermore, theoretical advancements in physics, particularly in areas such as quantum gravity and string theory, could provide indirect evidence. The development of a unified theory that consistently predicts the existence of a multiverse would lend significant support to the hypothesis. However, this requires breakthroughs in our fundamental understanding of physics, pushing the boundaries of theoretical research. Finally, the development of new observational techniques and technologies holds the potential for future breakthroughs. The development of next-generation telescopes capable of detecting extremely faint signals could potentially reveal anomalies or patterns consistent with the existence of other universes. Advances in particle physics and gravitational wave detection could also provide indirect evidence. It's important to acknowledge that testing multiverse theories requires overcoming significant obstacles. The inherent limitations of our observational capabilities, coupled with the speculative nature of these theories themselves, make definitive proof elusive for now. However, the ongoing pursuit of these explorations reflects the vitality of scientific inquiry, constantly pushing the boundaries of our understanding and expanding our capacity to explore the universe's deepest mysteries. The quest to test the multiverse hypothesis, therefore, is a frontier of scientific inquiry that demands both imaginative theoretical exploration and increasingly sophisticated observational methods. This leads us to a discussion of the methods used to measure cosmic distances. Measuring distances across the vast expanse of the universe isn't a simple task. We can't use a ruler or tape measure to determine the distance to a galaxy billions of light-years away. Instead, astronomers employ a sophisticated multi-step process, often referred to as the cosmic distance ladder. Each rung on this ladder represents a different method for measuring distance, building upon the previous one to reach ever greater distances. The first rung, the most direct method, involves parallax. This technique utilizes the apparent shift in a star's position as observed from different points in Earth's orbit around the Sun. By measuring this tiny angular shift, astronomers can calculate the star's distance using simple trigonometry. This method works well for relatively nearby stars, but becomes less accurate at greater distances. The next rung employs standard candles objects with a known intrinsic luminosity. By comparing a standard candle's apparent brightness to its known luminosity, astronomers can estimate its distance. Cepheid variable stars and type Ia supernovae are commonly used as standard candles. Cepheid variable stars pulse regularly at a rate that's related to their luminosity, allowing astronomers to infer their true brightness. Type Ia supernovae, on the other hand, have a nearly uniform peak luminosity, making them excellent standard candles for measuring larger distances. The following rung utilizes redshift. As discussed earlier, the expansion of the universe stretches the light waves from distant galaxies, shifting them toward the red end of the electromagnetic spectrum. The amount of redshift is related to a galaxy's distance, providing another method for estimating its distance. However, this method requires careful calibration and assumes a well-understood model of the universe's expansion history, including the influence of dark energy. These three methods, parallax standard candles and redshift, form the foundation of the cosmic distance ladder. Each method relies on calibrations from the previous rungs, creating a chain of measurements that stretches across vast cosmic scales. This intricate process, however, is not without its limitations and uncertainties. The accuracy of each rung depends on the accuracy of the preceding ones. Any inaccuracies at the bottom of the ladder propagate upward, affecting the accuracy of measurements at greater distances. Moreover, different measurement techniques can yield slightly different values for the Hubble. Constant the universe's expansion rate, a critical factor in redshift calculations. This ongoing refinement of the cosmic distance ladder highlights the challenges and complexities inherent in measuring distances across cosmological scales, underscoring the constant evolution of astronomical techniques and models. This leads us to a discussion of the different types of cosmic distances and their implications. Measuring distances in our expanding universe isn't as straightforward as it is in our everyday experience. The expansion of space itself alters the meaning of distance, introducing complexities that require careful consideration. Several different measures of cosmic distance are used, each offering a unique perspective on the vastness of the cosmos. One common measure is co-moving distance. This represents the distance between two objects at a particular moment in time. Assuming the expansion of space is frozen at that moment. Imagine taking a snapshot of the universe. Co-moving distance would be the distance between two galaxies in that snapshot. Co-moving distance is often used to compare distances between objects at different times because it provides a consistent frame of reference that isn't affected by the ongoing expansion of space. Light travel distance, on the other hand, represents the distance light has traveled from a distant object to reach us. This distance corresponds to the age of the light expressed in light years. If we observe light from a galaxy that's 10 billion years old, then the light travel distance is 10 billion light years. This measure is tied to the time the light has been traveling, but doesn't account for the expansion of space during that journey. Angular diameter distance is a measure related to how large an object appears in the sky. Imagine looking at two objects of the same physical size, but at different distances. The closer object will appear larger than the farther object. Angular diameter distance incorporates this perspective effect, accounting for how an object's size changes with distance. It's a useful measure for determining an object's apparent size in the sky. Luminosity distance is related to the apparent brightness of an object. A light source's apparent brightness decreases with distance. Luminosity distance accounts for this dimming effect, allowing astronomers to estimate an object's intrinsic luminosity, its true energy output based on its apparent brightness. This is particularly useful for standard candles objects with a known intrinsic luminosity, which help determine distances. Finally, it's important to consider that these distance measures are all interconnected and interdependent, affected by the universe's expansion rate and its overall geometry. The relationship between these different measures is complex and requires sophisticated mathematical models to account for the effects of cosmic expansion. Because the expansion of space is not constant, but has accelerated over time, choosing the appropriate distance measure is crucial for accurately interpreting cosmological observations, highlighting the complexities involved in measuring distances in a dynamic and expanding universe. The choice of distance measure, therefore, is essential for interpreting cosmological data, revealing the intricacies involved in charting the cosmos. This intricate process of distance measurement allows us to explore the universe's potential topology. Let's investigate the fascinating possibility of a universe that loops back on itself. Our everyday experience shapes our intuition about space. We perceive it as a three-dimensional expanse extending infinitely in all directions. However, the universe's true topology, its overall shape and connectivity, might be far more complex and less intuitive than our common perceptions. The possibility of a universe that loops back on itself, a concept explored in the field of topology, challenges our understanding of cosmic geometry and the nature of space itself. Topology, in essence, is the study of shapes and their properties under continuous transformations. Imagine stretching, twisting, or bending a shape without tearing or gluing it. Topology focuses on the properties that remain unchanged under these transformations. A coffee mug and a donut, for instance, are topologically equivalent because one can be continuously deformed into the other without breaking or gluing. The presence of a hole, a single continuous surface, is what makes them topologically equivalent. Applying this concept to the universe raises profound questions about its overall shape and connectivity. Our observable universe appears relatively flat on a large scale, but this doesn't preclude the possibility of curvature or even looping on scales beyond our current observational reach. If the universe is finite, then it could be shaped like a three-dimensional sphere, a torus like a donut, or a more complex multi-connected shape, all without having any edges. One approach to investigating the universe's topology involves searching for repeating patterns in the cosmic microwave background (CMB). If the universe loops back on itself, then the light from distant objects could travel around the universe and reach us from more than one direction, potentially creating repeating patterns in the CMB. While no such patterns have been definitively detected, the analysis of the CMB's detailed structure remains an active area of research. Another approach involves searching for ghost images of distant galaxies, faint duplicates of galaxies appearing in different parts of the sky because their light has traveled along multiple paths through a looping universe. However, detecting such subtle repeating patterns in the noisy cosmic background presents immense challenges. Moreover, the universe's accelerating expansion driven by dark energy complicates the investigation of its topology. This expansion not only pushes distant galaxies beyond our observational reach, but also affects how light travels through space. The expansion of space itself might obscure any subtle topological features of the universe, presenting an additional challenge to the ongoing efforts to map the true shape of the cosmos. The exploration of the universe's topology, therefore, is a complex endeavor requiring sophisticated mathematical tools, subtle observational techniques, and innovative data analysis. The possibility of a looping universe continues to be an active and fascinating area of cosmological inquiry, pushing the boundaries of our understanding of cosmic geometry and the very nature of space itself. The quest to unravel the universe's topological secrets remains a significant challenge, yet it holds the potential to reshape our understanding of reality itself. This exploration of the universe's potential shapes naturally leads to a discussion of its possible ultimate fates. Let's consider the various scenarios for the universe's ultimate destiny. The ultimate fate of the universe is one of the most profound and challenging questions in cosmology. The answer depends critically on several factors, including the universe's overall shape, its density, and the nature of dark energy. While we don't yet have a definitive answer, several compelling scenarios have been proposed, each offering a unique vision of the universe's ultimate destiny. One possibility is a Big Freeze scenario, often considered the most likely outcome given our current understanding of the universe's accelerating expansion. In this scenario, the universe's expansion continues indefinitely, driven by dark energy. Galaxies move ever farther apart, eventually becoming isolated islands in a vast, cold, and dark expanse. Stars burn out, black holes evaporate, and the universe gradually approaches a state of maximum entropy, a state of thermal equilibrium, where energy is evenly distributed and no further significant change occurs. This heat death of the universe would be a slow, gradual process spanning trillions upon trillions of years. If the universe's density were higher than the critical density, the precise density required for a flat universe, then gravity might eventually overcome the outward push of expansion. In this case, the universe could slow its expansion, eventually halting, and then beginning to contract, leading to a Big Crunch scenario. In this dramatic reversal of the Big Bang, the universe would collapse in on itself, becoming progressively hotter and denser until it potentially reaches an infinitely dense singularity. This scenario would be a violent and final end to the cosmos, erasing all structure and potentially leading to a new beginning, a cyclical repetition of cosmic birth and death. Another dramatic scenario is the Big Rip. This would occur if dark energy's density continued to increase over time, eventually surpassing the strength of all other forces, including gravity. In this scenario, the accelerating expansion would become so powerful that it would rip apart galaxies, stars, planets, and even atoms themselves, ultimately leading to the complete disintegration of the universe's structure. The universe's ultimate fate, therefore, is intimately tied to its shape and density. A flat universe, as suggested by current observations, would likely undergo a big freeze, while a universe with a higher density could potentially end in a big crunch. The possibility of a big rip, on the other hand, remains a significant area of ongoing research. Regardless of the specific scenario, pondering the universe's potential endings leads us to confront fundamental questions about time-space and the very nature of existence, underscoring the vastness and enduring mysteries of the cosmos. The journey to understand the universe's ultimate destiny is an ongoing scientific quest, highlighting the interplay between observation theory and the profound mysteries that continue to captivate scientists and thinkers alike. The unknown future of the universe remains a source of both wonder and speculation. This exploration of cosmic scales and potential endings leaves us with a profound sense of both awe and uncertainty. What more can we learn, and what new questions will emerge as our understanding of the cosmos continues to evolve? Only time and further exploration will tell. Our understanding of the universe is profoundly shaped by both observable limits and theoretical possibilities. From the finite speed of light to the accelerating expansion driven by dark energy, our capacity to observe the cosmos is inherently limited. Yet these limitations fuel our exploration of profound questions about the universe's size, shape, ultimate fate, and the tantalizing possibility of a multiverse, demonstrating the power of scientific inquiry to navigate the unknown.